Okay, so conceptually we've looked at Newton's three laws. From a problem-solving and practical standpoint, really the law that you use the most is Newton's second law. So typically what you're using is F net is equal to ma. In each one of these cases that we're going to look at, the very first thing, and you know this already, but I'm going to restate the obvious, the very first thing you're going to do is you're going to draw a force diagram. Now, one of the things that you guys need to understand is anytime we draw a force diagram for something that's only in translational motion, meaning traveling in a straight line, there is a big assumption that we make. And that assumption is that all of the force is applied through the center of the mass. Now you know enough now that if we apply a force off the center, we're going to cause this thing to rotate. We're going to cause it to torque. And a lot of what they do with you initially on paper 1 and paper 2, actually not a lot of it, all of it is translational motion. They're only looking at straight line. They're not going to do any rotational motion until paper 3. So they actually keep them separated for you. So our assumption is that all of our forces are passing through the center of mass of this thing. We're not going to cause it to spin. We're only going to make it go in a straight line. So that's first things first, right? Translational motion only. Let's take some basic examples of some problems that you've seen in the past. And there are buzzwords that you need to look for. And if you don't look for these buzzwords, you will not get the problem, right? So all of these buzzwords tell us about this net force. So buzzword number 1, right? Constant velocity. Or at rest. If those two words appear anywhere in the problem, they're telling you that the net force is equal to 0. And if the net force is equal to 0, then the acceleration also has to equal 0. So what you're going to then do is look for all the forces to balance. Up balances down, right balances left, or whatever direction or whatever kind of scenario that they have. Those are buzzwords you must look for. If, however, they say that there's any type of acceleration, if they use the word acceleration, it's on you to draw a force diagram and identify the net force. Who's winning the tug of war and by how much? Let's go through some familiar problems that you've done in the past, I hope, and let's take a look at some of these. One of the most missed problems is the elevator problem, right? It's classic. And what they do is they put somebody in an elevator and they put them on some type of scale and they stand the person on it, right? And they give some information. So let's just say for grins, at rest, right? This person has a mass of 80 kilograms, has a mass of 80 kilograms. And the question becomes, okay, the elevator rises, let's say, with an acceleration of 2 meters per second squared. And they say something like, what does the scale read? Now, you can kind of dope this out if you have some experience. So let's just use some common sense, what I call Robert E. Lee approach. He was a very creative person, as opposed to Ulysses S. Grant, who was very straightforward, concrete, sequential. Ulysses S. Grant was an equation guy. Robert E. Lee was not. So let's think about Robert E. Lee first, right? If this thing rises up, if you've ever been on a fast-moving thing upwards, it feels like you're sunk to the bottom, right? It's almost like you feel like you're pushing harder down on the ground. So you would probably expect the scale to read higher. Those of you that are creative could probably use this to get the answer. Now, you should know that if this thing is at rest, right, and I draw a force diagram for this guy, he's going to have his weight downward. And guys, just for simplicity's sake, I'm going to use 10 meters per second squared for acceleration due to gravity. Okay? So if I use that for G, then this guy's weight is going to be 800 newtons downward. How did I get that? M times G, I took his weight, or his mass, excuse me, multiplied it by 10. If he is at rest, that means these forces are balanced. That means the force of the scale upward on him, right? Or the normal force of the scale has to also be 800. So that means the scale is going to read 800 newtons. Okay? That's if he's at rest. But that's not the case. This guy is accelerating. Now I need you to think about it. This picture changes. This picture changes. Let's not even say normal force. Let's say the force of the scale on this guy, just so we can identify what that thing's coming from. So right now they're equal. They're balanced because this guy's at rest. But now it's accelerating. So if I draw a force diagram on the guy now, it's different. I've got still his 800 newtons downward, right? It's still being pulled downward. His weight is normal, what it was. But he's going upwards. He's accelerating upwards. Acceleration. That's one of my key buzzwords. That means there's a net force. Somebody's winning the tug of war. And if he's going upwards, the tug of war is being won upwards. So now the force of the scale, which I'm going to represent with a longer arrow, is bigger. It's winning. So if I read this thing, I'm going to say, okay, the force of the scale is beating his weight. So far, so good. How much is it? Well, I don't know. I don't know this value. But I do know that Newton's second law says if you know the net force, who's winning the tug of war and by how much, it's equal to his mass, 80 kilograms, times his acceleration, 2 meters per second squared. Now the math becomes simple. On this side I get what, 160 newtons? This is still 800 newtons. And so if I solve this thing for the force of the scale on him, I add these two guys, and I'll write it up here. I get 800 plus 160, I get 960 newtons. So now that scale is going to read bigger, right? Because the floor is literally pushing up against his feet, and it looks like the spring scale is pushing him up, and so it's got to be bigger. How much bigger? Well, it's 160 newtons bigger to get him to accelerate that much. So it looks like his weight has gone up. Conversely, if this arrow was downward, that would mean the weight is winning. And we would play this game the exact same way. But you notice, I've got one guy, I've got one force diagram, I've identified who's winning the tug of war and the direction, and I've set up my Newton's second law equation to show that. Okay? That's number one. Let's look at another problem they expect you to know. And it's a simple one. It is a ball falling through a fluid. Right? Everybody needs to know this. Standard and higher level. Falling through a fluid. Water. You take your pick. If it's falling in a vacuum, we know darn good and well that if this ball has mass m, the only force on it is downward. Everybody's cool with that. If it falls through a fluid, however, there is an upward force. And this upward force, you know it as drag. Drag. And that drag force actually has a name. Now, higher level needs to know this, so I'm at least going to throw this in. Standard level, you've seen this before. This drag force, we can actually calculate it, right? We use something called Stokes' law. This is a higher level thing, so don't freak out standard. You still need to know the basics, just not this specific. The drag force is dependent upon, let's see here, it's dependent upon that, which is the viscosity of the air, okay? It's dependent upon the cross-sectional area. So what we're talking about is basically, as this thing falls, you see an area of a circle as it falls, right? If I turn it on its side, all you see is that. That's the area that we're talking about. How do you calculate that area? Well, let's see. It's a cross section, so it'd be what, pi r squared? I think I've got that correct. The other thing that it's dependent upon is the speed of the object. How fast is it falling? Now, if that's the case, all of you now need to see this connection. When you first drop it, well, the viscosity of the fluid doesn't change, the cross-sectional area doesn't change, but the velocity does. As this thing falls faster and faster and faster, this drag force begins to increase and increase and increase. And it increases because of this velocity. Ultimately, what happens is you will have this thing fall in such a way that it falls at, yes, you know the term, terminal velocity. So the terminal velocity is that speed when, you got it, the net force is zero. It's falling at a constant velocity. If it's falling at a constant velocity, that means the forces are balanced. And when it falls, that means mg is equal to this drag force. And the graph of this thing, not the force, mind you, but the velocity as a function of time, looks like this. It speeds up, it speeds up, it speeds up, and then it levels off, and then it flattens. During this part is the terminal velocity. During this part is where this velocity is growing. They expect all of you to understand that very basic understanding. Okay? And that's anything falling through. Now, you can see that if you've got something that's not regularly shaped like a sphere, let's say you drop a cube. What happens is that cube becomes kind of unbalanced in the air and it tumbles. And as this thing tumbles, the cross-sectional area changes. So this thing behaves weirdly, and that's why when you drop irregular shaped objects like a human or a piece of paper or a feather, they tumble and do strange things. That's why in all of the problems we deal with, or all the labs that we have you deal with, we deal with spheres because they're regular shaped, and even if they tumble, doesn't matter. They always present the same surface area. Okay? Terminal velocity. Let's take to your favorite, an incline. Just a quick refresher. All inclines are the same, regardless if they're frictionless or friction filled. So here's an incline. It's got a box on it. And that box has mass m. Now, what I tell my classes when I teach Physics 1 is you can change your coordinate axes to fit the situation. And literally that's what we do. So if you look at this picture, you do what I call the Cocker Spaniel head tilt. You know, when you talk to a dog and it tilts its head, tilt your head until it aligns with kind of the axis of the normal, if you will, of the inclined surface. In doing so, what you've done is you've just basically rotated your axis, where this is your normal x and this is your normal y. Why have you done that? Because all of the motion is going to be along here. So you might as well make your picture and your axes match that. When you do this, if we simply look at the forces acting on this box, weight always acts straight down, right? And you'll notice that it's not along these axes that we just drew. It's actually acting at an angle, right? That means that gravity on this incline is doing two things. And what the incline basically does is it dilutes gravity, right? Inclines dilute gravity. Dilutes gravity, if you want to think of it that way. And what it does is it takes and splits it into two separate parts. There's a piece of it, and if you, I don't know if you can see it, how well your geometry is, but there's a right triangle right here, right? And here's the angle. And I think last year when Glidewell taught you this, and when you draw this force diagram, draw it in the same orientation. There is part of this that is pulling it down the incline. It makes it slide. It's this aspect. This is the opposite side on this triangle. And it's diluting the weight. So it's the weight times the sine of theta. Sine slides down, I think is how most of you remember this. There's another part of gravity that is literally holding it to the incline. And that's the other part of gravity. That's mg cosine theta. Now, right away, if those were the only two components acting on this box, it would fall this way, straight down. It's not doing that. You know that the motion is restricted to sliding up and down the incline. So right away, you know that vertically there must be another force. And that force is the push of the surface, or the normal force. And the normal force and mg sine theta are the same, exactly the same. If this is a frictionless incline, then this block would slide straight down. It would translate straight down the incline. You could actually calculate its acceleration, right? Who's winning the tug of war here? Well, it's not these two, because they're the same. This guy's winning the tug of war. So that means F net is equal to ma. I always go back to this equation. Who's winning the tug of war? mg sine theta. By how much? Well, there's no other force, and that's equal to ma. Real quickly, you can see that the m's cancel. It doesn't matter if we're sliding a big box, a little box, a tiny box. The acceleration down that incline is g sine theta. Now, I want you to think about this for a second. So, as I continue to increase this angle, and increase this angle, sine of theta gets bigger and bigger and bigger. Well, just imagine that I increase that angle to 90 degrees. And I've got my block here. What's it going to do? Well, sine of 90 is 1. So basically, this thing falls. And that's what we would expect. This picture is going to be the same for everything on an incline, period. Period. What's going to change is if there's friction involved, if there's tension involved, or something of that nature. If this incline, and I'll redraw a new one here so we can make it a little cleaner. If this incline had friction of some type, and this box is on it, and if it's sliding down the incline, right? Slide down, let's say. Those three forces are there. mg, and you can always do this. mg sine theta, normal force, mg. Those are always going to be there. If it's sliding down the incline, then you know friction is always going to oppose the motion. So if it's going down the incline, that means friction has to be back this way. Now we can calculate the acceleration. Well, who's winning the tug of war? Well, if it's going down, it's this guy, mg sine theta, minus the force of friction has to equal ma. You can go a little bit further. I don't know if you remember this. This is an appropriate place to put it. The force of friction depends upon how rough, if you will, the surface is, the coefficient of friction. And if it's moving, we call it the coefficient of kinetic friction. And the normal force, right? The push of the surface on the box. Well, here we go. This is mg sine theta. This guy's mg, sorry about that, cosine theta, right? That's the other component that holds it to the incline. Since it's not jumping off of the incline or falling through the incline, these two guys must be the same. So now I can make a substitution over here and say mu k times the normal force, which is mg cosine theta. That's how we calculate the force of friction. Now I can plug that in here. So I have mg sine theta minus mu k times mg cosine theta is equal to ma. Again, here's the cool thing. Doesn't matter how big the box is. And notice we're not rolling anything, because if we roll it, a whole nother thing comes into play. These are all sliding. This is translational. So basically, what do you need to know? You need to know the angle, how rough the surface is, and you can find and gravity, what planet you're on, and you can find the acceleration. Does this change if you slide up the incline? Ooh, that's an awful incline. Sorry about that. Well, if you slide up the incline, what changes? Guess what doesn't change? Those same stinking forces, components, if you will, of the forces. This is still mg sine theta. It always pulls it down the incline. Whether it's going up the incline or down the incline, this is always holding it to the incline. This is always going to be there because the surface has to hold it up. Now what you have to decide is, okay, if it's sliding up, friction always acts to oppose the motion. Oh my goodness, that must mean it's down. How does this change what we just did? It really doesn't. Now you have two forces that are winning the tug of war. They're going to slow this thing down. So you're going to have mg sine of theta plus the force of friction now, not fighting one another, helping one another, is equal to ma. Net force is equal to, here's the net force, is equal to ma. It's that same game, guys. The force of friction is the coefficient of friction times the normal force. And the normal force is going to be the same, mg cosine theta. So it's the same force. All we're doing is adding it now because it's helping, right? So we have mg sine of theta plus mg cosine theta is equal to ma. Again, look what happens. M's kill. And this time the acceleration is going to be bigger because there's a plus sign there. These two guys are helping one another, so they're going to slow down the box a lot faster than if you slide it down the incline. Okay, that's the basics for an incline. Now, let me take one more system, and it's a pulley system. And I know I'm running just a little bit long. I'm trying to keep these to 20 minutes, but trying to get everything into this is going to take a little bit longer. The last system is some kind of a pulley system, okay? And one of the toughest ones, for some reason, for students is this. You have something sitting on a, let's say it's a, I don't know, a frictionless incline. We'll make it easy. And it runs over a pulley. And there's a little box here that's much, much smaller. M is much, 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 much smaller than the big mass on the table. And this is frictionless. Couple of things I need you to understand. If they say that the pulley is massless, then you don't have to worry about the pulley. Okay? And again, on paper 1 and paper 2, all of the pulleys are going to be massless. So you don't have to worry about its rotational inertia, and you don't have to worry about the torque on it. It's strictly going to be a translational problem. And the purpose for the pulleys, the sole purpose for the pulley, is to redirect the string, to change the direction of the pull of the string. It's not involved in the system because really it's not there. There's no such thing as a massless pulley. They'll also say that they are massless cords as well. And there's no such thing as a massless cord. Here the system's a little bit different than the last one we did. How many bodies do you have? You have 2. So that means you're going to have to use Newton's law twice. That means you're going to have 2 force diagrams. You're going to have to do everything double. The other thing that you're going to have to do is somehow connect these two. Well, it's already done for you. This is what connects them. It's the string. All right, so let's draw a force diagram for the first one. It's, let me see, got the weight because we're here on Earth, big M, right? We got the normal force. We got the push of the surface. Anything else? Well, it's frictionless, so there's no friction on it, but there's a tension this way. Now, I want you to look at that picture because most people say, oh, if this mass is so much smaller than this one, that thing can't move it. That's true most of the time, but this is frictionless. Look at this diagram. Well, it's not falling through or not jumping off of the surface. These two guys must be equal. But look, there's only one force, T, an unbalanced force that's affecting the system. If there's an unbalanced force, Newton's second law says there's got to be an acceleration. So I can write Newton's second law for this. T is equal to ma. There we go. Already got an equation. Let's look at this little guy. If we say he falls downward, right, that means somebody's winning the tug of war. There must be an acceleration. If I draw the force diagram for this, let's see what we've got. I've got little mg down, and I've got T upwards. These guys can't be equal, because if they're equal, this guy doesn't fall. And if this guy doesn't fall, this guy doesn't move. But we can see right here, he's going to move. So So automatically, if we know that this is accelerating downward, this guy has to be winning the tug of war. So we're going to say little mg minus t is equal to little m times a. And here's the cool thing. If it's a massless cord, if it's a massless pulley, this tension and this tension are going to be the same. Because all we've done is redirect the direction of that force because of the pulley. The pulley's not involved. Here's the other thing. If this guy's accelerating, this guy's accelerating at the same rate. So they share acceleration and they share tension. So if I make a substitution, I'm going to have mg minus, and I'm going to plug in what I have for that. T is equal to big MA, right? That's what this guy, I'm just plugging it in up here, is equal to little ma. Well, the whole idea for this is for me to figure out the acceleration. That's the kind of question they're going to ask you. So if I take this across, I'm going to have big M A plus little m A is equal to mg. And if I factor out an A and divide, I get mg over big M plus little m. Well, let's see if this sucker makes sense. You ready? Let's say for grins that, what do we want to do? Let's say big M is really small. Let's make big M 0. If that's 0, that disappears. And I have mg over m. Well, the m's cancel, and it says, oh, the acceleration of this guy is just g. It's basically you've cut the string, right? If this has a mass of 0, it's like you've just cut the string. Let's go the other way. What if this mass is really, really, really big? I mean, really, really big. That makes this denominator really huge, which makes this number really small, which makes the acceleration very small. I think that makes sense to you, right? This tension is whatever it can be. And that tension, if it's pulling on a really big mass with a really big inertia, its tendency to stay at rest. It can't, though, because there's nothing pulling backwards against it. So it's going to go, but it's going to go with a very, very tiny acceleration, because this little old mass can't get this guy speeding up very quickly. But it's going to get it moving. And if it falls long enough, it'll get it moving very fast over a long period of time. This is what we do in space. We launch particles out the back of rockets. And each little particle that goes out the back gets it moving forward a little bit. And the more particles we launch out the back, the faster it gets going, because there's nothing to slow it down in space. Okay. So guys, I've taken you through just about every type of basic problem, but they all share the same thing. You do number 1, you look for signs. Constant speed, net force is 0. Rest, net force is 0. Draw a force diagram, all the forces should balance. If it says acceleration, somebody has to win the tug of war, and you have to use Newton's second law. Who's winning the tug of war, and by how much? By how much? The only way you can find that is by subtracting, and that has to equal ma. We're using Newton's second law over and over again. I don't want you to memorize types of problems. I've chosen different problems or different types of systems so that you can see how they apply. Don't memorize the system. Memorize the procedure. Draw the force diagram. If somebody's winning the tug of war, write the equation, set it equal to ma. If they're not, the net force is 0, and go from there. Okay? All right, so that's applications. I've got a packet for you. We'll see how this works and if it helps you. Okie doke.